to learn today recursion. Okay? What is recursion, guys? Have you ever heard before? Do you know what recursion is? Yes, say it. What's recursion? If you've done that already. No idea yet?
When something calls itself. So
When something calls itself. Okay? Give me an example of that.
Google recursion.
Yes.
No, I mean that's
It's going to give me the same name. Yeah. Yes.
like a method calling itself.
Okay, if you're talking programming way, yeah, it refers to a method calling itself. Sounds kind of stupid, right? How am I going to call something myself, right? So, I'll give you an example. Assume we want to paint these tables, okay? And somebody calls me the method paint. Maybe there is a method paint to perform that job, say paint. And provides me the length of the table, okay? Now, let's say this length is, I don't know, roughly, say 5 inches. So 5 feet. Roughly 5 feet, okay? Now, I know how to paint 1 feet. If somebody would send me paint with 1 feet, I would do it. I would take my brush and paint 1 feet. I'm trained to do that, right? But now, somebody's giving me a table that is 5 times that, so I cannot do it, right? It's straightforward, I cannot do it, right? Because I'm trained to do only 1 feet, right? So what do I do now? So the idea is that you do this. Assume, okay, that somebody else, there is some magic function out there, somebody else out there is capable of doing the rest. So you do whatever you know how to do, okay? And don't worry about the rest. You do whatever you know what to do. So you paint 1 stripe of 1 foot, and then I call the same method paint. Assume somebody else is going to do that with the rest, with 4 feet. Got it? Now, am I solving the problem completely? No. It's like I'm evading the problem, right? I'm doing one part and giving somebody else to do the rest, right? Correct?
Yeah.
Now, but that somebody else is actually myself. Now I'm receiving the job of painting a table with 4 feet. What will I do? The same procedure. Paint whatever I know how to paint. 1 foot again. And call paint myself now with 3 feet. Isn't my problem getting smaller and smaller each time? Right? It will get to a point where I get just 1 foot. And that's exactly what I know how to do. I paint that and I'm done. Because there is nothing else to be done. Right? You understand the idea? No. The idea is to have a big problem, and start reducing it, until it becomes so small, so trivial, that I know the answer up front. All of you remember the factorial, right? The factorial is a perfect example to explain recursion. All of you know factorial?
Yep.
Right? If I tell you factorial of 5, what is factorial of 5? This is 5 times 4 times 3 times 2 times 1. That is easy, right? 120, right? Now, isn't all of this at the same time is factorial of 4, right? So I can define 5 factorial as 5 times 4 factorial. If you put this as methods or functions, you can write fact of 5 equal 5 times fact of 4. Right? Correct? Now, isn't your function or method calling itself, but with a smaller problem now?
Yeah.
Right?
Yep.
Isn't it like that? Now, the factorial has this behavior. If I tell you factorial of 100, obviously your brain is not going to compute that as like this, right? Unless you already knew the answer in advance, right? But if you put in a piece of paper and you start solving it like that, you can say 100 times factorial of 99, then 100 times 99 times factorial of 98, then you can multiply 100 times 98 is 9900, right? Correct? And you can start doing the multiplications like that, right? Now, if the numbers, if the factorials were not clearly defined, you will never finish. Because once you go to 0, you will go to -1, -2, -3, and numbers are infinite, right? Now, how is the factorial defined? The factorials are only defined for numbers greater or equal to 0. You don't have factorial of -5. That does not exist, right? Now, the stopping condition, when I'm going to stop going backwards and backwards and backwards, is when I get to factorial of
0.
If I tell you factorial of 0, what's that? 1. That's a fact, right? So the idea is to have the big problem, start reducing until you find one small set that is so small that you can give me the answer up front. Got it? I'll write it right here, okay? You prefer black or red, guys? Because the black is kind of bad. Red is fine? Okay. Let me put here an example. Say factorial of 3. Actually, I will write this with fact. Factorial of 3. What is factorial of 3, guys? It's 3 times factorial of 2. Right? Now, this guy. Now my problem is factorial of 2. What is factorial of 2? Am I giving an answer already? Not yet, right? I'm not giving an answer yet. Now, what is factorial of 1? What is factorial of 0? Here's where you can stop. You know your answer already. You say 1. Right? You don't have to keep going anymore. Now, how would we write this in a method? Well, let's call it public. All methods start with public. The factorial returns what? A string, a char, or what? What does it return? Right? Let's call it fact. That's fine. And what do you need to receive? An integer, right? A number, right? In n. Okay? For now, just for now, since your guys are starting, get used to putting the base condition or the stopping condition first, as the very first thing in your method. Okay? Do you have to put that as the very first thing in a recursive method all the time? Not all the time, but it's easier when you are starting. So, what is your stopping condition or your base case? How do you come up with that? You think what the problem is. In this case, the problem is how to calculate factorial. The next thing you understand, after understanding what the problem is, you understand. You start thinking, under what input could I give the answer up front without thinking? 0. If you tell me 1,000, then you're a genius, right? Nobody can tell the factorial of 1,000 like that, right? So you say, okay, when you give me 0, I can give you the answer without thinking, right? So you say, if, you write like that, if you give me 0, if n that you give me is 0, I can return the answer to you without thinking much. Return what? Right? Else, do you need an else here, guys? No, because if it's not 0, you're going to just jump to the next line anyways. You don't need the else. You know that, right? Okay, else what? You should return what? You should return n times the factorial of n minus 1. Isn't that like that? If you give me 3, I would return as my answer 3 times the factorial of n minus 1. Got it? Yes? Is that clear? And this is the solution for creating the factorial recursively. Looks simple, right? Yes.
What were you saying at the beginning that we should do as beginners?
As beginners, think of your stopping condition and put it first before doing the recursion.
Oh, okay.
Here's your recursive call. You see you're calling fact again.
Okay.
But before calling fact, your recursive call, put your stopping condition first.
Okay.
Okay? And why is that important? Because if I put this first, what happens if somebody gives me 0? I will return 0 times factorial of minus 1. And I'm screwed already. Right? Now, let's analyze how this code works. Because it looks like I'm here and I'm calling myself and I will have to go back here, right? Looks like that, right? Let's see how this works. So, you say 3 times factorial of 2, 2 times factorial of 1, 1 times factorial of 0. Now, when I say factorial of 3, I'm giving these results, right? These results coming from here, right? Correct? Java, the way it works, Java says, okay, the answer is this, but it's not a final answer, right? Because this has to be evaluated, correct? So Java puts like a question mark here, like, I'm on hold. I cannot give you an answer yet. I need to know what that is, right? And puts that in memory, in a stack of memory. In memory, Java stores this partial result, which is 3 times factorial of 2. It stores that result partially. It has to store it. because now Java has to evaluate this, right? And assuming Java knew the answer of this, now it has to go back to what it stored before so they can give the final answer. Is that clear?
Yeah.
Yes? So Java puts this and puts a question mark. Now Java evaluates factorial of 2. It's fine. This has been saved already, right? And says, factorial of 2 is 2. It checks. Is 2 equal to 0? No, right? So the answer will be again this one, right? 2 times factorial of 1, right? So Java checks. Is this a final answer? No, because I have to evaluate this. So Java puts another question mark here saying this is pending. And we'll store this in memory. 2 times factorial of 1. Got it? Now, Java says, okay, this is my job now. N is 1, right? Is 1 equal to 0? No. I'll have to do this, right? So this will give me 1 times factorial of 0, right? Correct? And this has to be evaluated, so I'll put a question mark here. Right? Now, my problem now is factorial of 0. N is 0. Is 0 equal to 0? Yes. So this returns 1. So I get an answer now. Sorry, I forgot to put here 1 times factorial of 0, right? Correct? Now, factorial of 0 evaluated, that gives me an answer, 1. Right? So Java says, now I will take out whatever is on the top of my stack. This result was the last one that was stored, right? It says, now I should be able to replace it. So factorial of 0 was 1, right? I will replace 1. 1 times 1, and replaces this with 1, and this is gone from the memory. Okay? Now Java says, now that I know this partial result, I should be able to evaluate this and replace this into whatever I had pending, right? Correct? And we'll replace 1 into this. 2 times 1?
2.
2. So this is already gone from the memory because it took it out, right? Now Java says, I know the answer of this. I will pop up this guy now. 3 times factorial of 2 and replace my previous value. So we'll replace here 2, right? 3 times 2? 6. And we'll clean out the memory. The memory is free again. So Java now can tell you 6. And I will tell you the answer. Got it? What I want you to understand is the procedure, how recursion works. Every time you call recursion, it's like you're going down, down, and down until you hit your stopping condition. Okay? Once you have hit your stopping condition, you have to come back and start answering your pending results by plugging the answers that you get. Got it? It's like a ladder. You go down and now you're going back. Now, is recursion efficient? Professor, if I were to create a program to calculate factorial, should I use this approach or should I use the for loops that we have learned? Use the for loops. Avoid recursion at all costs. So why the heck are we learning? Right? Because some solutions are way easier to come up with recursion. Some of them are easier to solve with recursion. If you were to do them iteratively, which is for loops and whiles and the classic approach, they take longer to come up with. And sometimes they don't take that much time, so you don't really worry. But recursion is inefficient. Remember, with factorial of 3, I have to have 3 spaces in memory to record partial results, right? Imagine if I set recursion 1000, I'll have to store in memory 1000 slots, right? Correct? If I set factorial of 1 million, I could fill up my memory and make it crash. Got it? So not efficient at all.
So it's only good when you use numbers. Recursion.
No, recursion is good only when you have problems that are too hard to provide an iterative solution. Okay? There are problems that are extremely complicated to come up with for loops and while loops. Recursion are very easy to come up with a solution to them. Like towers of Hanoi. If you look it up on Google and see towers of Hanoi, you will see. I will not cover towers of Hanoi because I will kill you here. Towers of Hanoi. If you want to read on your own, read Towers of Hanoi. It's a classic problem.
Is that the one with like the
discs.
four, and then you gotta take it to each one and then okay, no.
It's like that. You have 3 here and you put discs. Right? You move.
Yeah.
It's not too hard, but I don't want to push you yet. Okay? Is it clear, guys? Yes? So let's code this program, okay? Let's code. Was not hard, right? That should work. Right, guys? Guys, if you want to see how things are going down, if then it's going up, you want to see that? We can make printouts. We are going to do printouts so that you can see what happens. Now, one approach that some people tell me is, Professor, if I would put my stopping condition to n equal to 1, is that correct? You understand what I'm saying?
No.
If you would say if n equal 1, then return 1, factorial of 1 is also 1, right? It has a benefit, but it has a drawback. The benefit is that if somebody tells me that it puts the stopping condition to n equal to 1, then I don't have to go all the way here. It would stop here. From here, I would say 1 and 1 this iteration. Got it? Save a little bit of memory, right? Seems good, right? We're saving, right? But what happens if somebody gives me 0? And then I cannot answer his question, right? Because I'm not going to 0, right? Correct?
Yep.
So that's why the stopping condition has to be very cleverly thought. So is that clear? Now, I'll give you something easy for you to come up with. If I tell you summatory, remember the summatory, guys? Right? Of n and n is 0 all the way to 10, for example. This is 1 plus 2 plus 3 plus 4 all the way to 10, right? The sum of the first n numbers, right? Remember? Give me a solution that is recursive for that. That should be a piece of cake. Yes, you have the answer. Tell me.
It's almost identical to what you have right there,
Yes.
except instead of n times fact, it's going to be n plus fact.
Not quite. There's something else you need to check. Okay, let's do it piece by piece. Just got the sum, right? What is my stopping condition? If I tell you the sum of the first 10 numbers, do you know the answer up front? Most likely not. If I tell you the sum of the first 0 numbers, do you know the answer up front? What is it? Right? So if n is 0, what is the answer?
0.
Right? Else would be the sum of the last element plus the sum of the rest. Right? That's it? Actually, it should be called something. Right? Disregard. Let's play with all our circles, guys. It's a little bit more complicated. Power. Okay, we know the answer up front, right? 2 to the 5 is 32, right? That's very simple. But let's create a method to calculate the power of n to the n, right? Recursive. You understand what I'm saying, right? Correct? So I would say, let me call it power. Power. You understand what I'm saying, right? Always, 100% of the time, think, what is the easiest combination of numbers I could have that would make it easier? What is the easiest input I expect that I can give an answer like this? If I tell you, for example, any m, say 5 to the 7th, do you know the answer up front? If I lower the exponent, is it easier? 5 cubed, 125, right? 5 squared, 25, right? 5 to the 1 itself, right? And then, what's the simplest one? 5 to the series 1, right? So, what I could do is, okay, I will think of my easiest exponent, right? So my easiest exponent is what? If the exponent is 0, I don't really have to think much. I know the answer up front is 1, right? Else, what? Sorry? Do an iteration?
It's not 0 when doing the calculation.
What would be the calculation? Yes, what would be the calculation? You're totally right. M times, okay, good. one. If you're saying 5 cubed, for example, 5 cubed. So it's not 1, it's not 0, so you have to do something else. 5 cubed isn't the same as 5 times 5 times 5. You take 1 away. What do you have now? 8 minus 1, right? So it will be the same as 5 times 5 squared. Got it? So it will be m, that's your 5, times the power of this same m, but now one exponent less. Got it? That will give you your 5 times 5 squared. This will be 5 times 5 squared. Right? The next time will be 5 times 5. Right? Finally, it will be 5 times 5 comma 0. And then that's going to give you 1, and then you stop. Is that clear? Yes? You run this code? How do you like recursion so far? Everybody seems it's easy, right?
Not that easy.
Don't underestimate recursion, guys.
With that, the answers are online. You can do that with prime, right? Use for prime numbers.
For prime numbers? Yeah, you can detect how many prime numbers are in a range with this. Are we using the range every time? Fibonacci. So let's see what other examples of recursion I can give you. Okay. Let's make your life a little more complicated. Okay? Yes, arrays, you love them, right? So, what's the max visually? 9, right? That's the max, right? Now, if I tell you to create a method to calculate the maximum, is that hard? For loops and comparing and updating the max, that's it, done. Right? But if I tell you calculate the max, calling yourself, right? Calling the method yourself, right? How could I do that? System of 9, max is maximum of this array. Now, I'll give you some hints. Maybe, just maybe, receiving the array alone is not enough. We might need some extra information.
You need the length.
Okay, we might need the length, which may be the same as a of length, right?
Oh, you mean like another parameter?
Yeah. Okay, let's start discussing, okay? Let's start discussing ways of solving it. It's a little bit more complex, right? Because now we have to play with array indexes and then we don't have nice memories from Java 1. Right? You have resentment and anger towards your previous professors, right? Maybe towards me as well after your exam, right? Always play with things that are small. They make it easier. So I have an array of size 4 with random numbers. I want to calculate the max, right? So, one way, just one way, could be to have something as the array in a starting position, pos. The first time it will be 0, right? Correct? Now, an array in a position seems simple, right? Correct? So what happens? What happens if the position, if there is one position only in the array? Let's say I give you an array like this. What happens if I give you an array of size 1? What is the max? If the array has size 1, what is the max? Position will be 0, right? And that would be your only position, right? So in this case, position would be equal to a dot length minus 1, right? Correct? In that case, they will be equal, right? Correct?
Yep.
So, if the position is equal to A length minus 1, meaning the array has just one element, what's the max? Itself, right? A at position or A at length minus 1, whatever you prefer, they are the same, right? Is that clear? Yes? Simple, right? Simple or not? Do you understand the idea? You think always, guys, always think of your easiest scenario. That's your base case. The scenario where you know the answer, like this, without thinking much. If I tell you what's the max and I give you an array of 1 million elements, you're going to be screwed, right? But if I tell you the array has size 1, what's the maximum? Well, the only element that you have there, right? You don't have to be a genius, right? So, and when do you detect that that's the case? When your pos is equal to your length minus 1, the last position, right? Correct? Correct?
Yep.
So your method, say public int max, you're going to receive an array in a position where it supposedly starts, right? Suppose it's initially here, right? So you ask, if my position is equal to my last element, then I don't have to think much. I know the max is already the guy at that position. Right? Correct? If this is not the case, and I have something like this, which one is the maximum? Well, you become lazy and use recursion. Say, would be whoever is bigger. This guy, the first one, the one at position pos, or whoever is after him. Right? Which one is larger here? I can do this claim. This guy, so the largest is whoever is larger. This guy or the largest of these three. Isn't that true?
Yeah.
Isn't that true? The largest is this guy or the largest of these three. Right? Correct? So that's what I will say. If A at pos is larger, or I can do this, temporary variable. Okay, I will use a temporary variable. Say, to my right. I will call it to my right. To my right will be the max of whatever is after pos. So we'll call recursion. Look, max of this current array, but now to the right of pos will be pos plus 1, right? Correct? And now I will say, if A of pos is larger than to my right, to whoever is larger on my right side, then my larger should be A of pos. Right? Else, my larger should be the one to my right. Or max right, whatever you want to call it. Got it? And that's it? Great solution, right? Interesting? I will call it there, okay? My handwriting looks like a doctor right now. Anybody here? That one. So, I'll do this. If my position is equal to the length minus 1, then last element, right? So it has just one element, right? Remember? So I don't have to think much. If the maximum is the guy at this position, right? Else, I'll do calculation. Okay? Max right. I'll calculate the maximum to my right. Okay? The maximum to my right. Okay? Somehow, let's assume magically it's given to me. There is a max right. Okay? Let's put it like this for now. Let's assume magically somebody's going to tell me the maximum to my right of pos. Is that clear? So which one is my maximum then? Well, if your A at pos is larger than your max right, then who's the maximum? Pos, right? Else, the maximum is the one that is the maximum from the right that somebody did magical. Right? And how do I calculate the maximum to the right? Well, it's calling maximum from 8, but now it's starting at pos plus 1. Right? Is that clear? Is that clear, guys? Yes? Oh, my bad. I did not specify the first position. The first position is 0, right? Remember? Yeah. Max is 9. You see? Okay.
No, I got it, but I was just wondering, do you have to have position pass? Can't you just say in position equals 0 and then do the if? Because essentially, the user can start later on in the array and they'll miss all the numbers before that.
The thing is, you're moving with pos, man.
Okay.
Otherwise, how do you have recursion? You're moving with pos, so you have to have it. Pretty much the idea is it's interesting, right?
So A dot makes -1, you're starting at the end.
Yes. Pretty much I'm working like this.
You're starting at the end.
I'm assuming if I have one array, right? So maximum here will be called on what? On the array A. In which position? Always you have to start from the very first position, right? 0, right? Correct? If you have one element only, length minus 1 is equal to this one, right? Because length is 1 minus 1, the first position is 0. That is the only position available, right? Correct? So in this case, the maximum is the element at position 0, A of pos, right? Correct? So far, so good? Now, but if this is not the case, that means that we have an array like this. Right? Correct? So the first if did not comply. So what I'm going to do is I'm going to say the maximum of the whole array will be the maximum of this guy versus the maximum of all these guys. This guy is what? A of 0. Right? Initially, I had this, right? Maximum of A starting at 0. That was the maximum of everything, right? But now I just want the maximum from here to here, right? So it will be the maximum of A, comma, 1. Right? So whoever is larger, A of 0, or this guy, will be the maximum of everything. Got it? Is that clear? The trick is that pos plus 1 is moving every time.
That's recursion.
So now, correct, that's the recursion. Now, when I want to find what's the maximum of this piece, because I need to do that for this part, right? I will say, this is my pos now. I will say whoever the maximum of this will be whoever is bigger, this guy or the maximum of this. Got it?
You just continue doing it.
Then,
Straight forward.
who's the biggest of all these?
So then that will be
This guy
A1,
or
A2,
the bigger of all
A3,
this?
A4.
You're getting it. Now, what's the bigger of all this? This guy or the biggest of all this? Right? Now, who's the bigger of these two? This guy or the biggest of this? Now, in this case, pos is equal to length minus 1. The maximum of this little piece is himself. So I will compare these two guys. With that, I will get the maximum of this guy, of this guy, of this
That's
side,
A minus 1.
and compare to this guy. Exactly. Is that clear? Yes?
Is that what you did there? You did.
You just compared one at a time?
Yeah.
Yeah.
3 minus 0 and 2 and 3.
Sorry?
When it goes backwards. If you're saying that if you do the -1, that's because of the stack.
Correct. Remember,
So you're starting all the way on the right and going left.
You're starting on the left and going to the right.
let me draw this, okay? Let me play with a very small array. let's say an array of size 3 maybe. Yeah, size 3 should be fine.
So Java codes it from the left as the last element.
It's not Java, it's how I'm coding it. I'm saying it's at 0. So the first time, these are the indexes. So far so good? I want to calculate the maximum, right? So I'm saying maximum, this is my first call. Maximum of A, the array is called A. In the first position, 0, because I want to calculate the maximum from this position. Everything, right? So pos is 0, right? I ask, is pos equal to the length minus 1? No, the length minus 1 would be 2. So that's not the case. So I'm saying, calculate the max of these guys. Calculate the max of that. I call it max right. Right? I say calculate the max of these guys. How do I calculate? So, and then I'm saying, compare A of 0, right? A of pos, this is pos, remember, don't forget, this is pos, right? Compare A of 0 versus max right. Okay? Compare 0 versus max right. Whoever is larger, put that as the maximum. Is that clear? So this will be the final answer. Right? Final answer. Right? However, this final answer cannot be computed at once, because max right is not a variable that is calculated immediately. This max right is a call to maximum again. Right? How do we obtain max right? Well, max right is the maximum of the same method, okay? The same method, maximum of A. Since it's to the right of the current pos, will be like that. Right? Correct? That's why it says pos plus 1. You get it? You're seeing it, right? Max right is the maximum of 8, but pos plus 1. That's why it says right. Correct? So, maximum of A1. Now my problem is, how do I calculate the maximum of these two, right? Of this array, right? Well, it says, is pos. Pos now is here, right? Now pos is here because it says 1, right? This is pos. Right? Is pos equal to the length minus 1? No. Pos is 1, length minus 1 is 2. So we are not playing in that case yet, right? Correct? Is that clear? So that's not the case. So say, okay, then the maximum is A of 1 versus the max right of this new comparison. Make sense? So now my maximum is this guy, or whatever is to my right, which in this case is one element, right? Now, this is, say, my intermediate step, right? Intermediate, right?
That's, A pos is greater than max right. That's what that is.
Correct. This part is evaluating the first recursive call. Now, my problem is, again, I cannot give this answer. If I had this answer up immediately, I would give it to this guy and build the final answer because I have this value, right? Correct? But I don't have that. I don't know what max right is. So max right here, I will call maximum, for the three max rights, I will call maximum on A. Since this was 1, pos plus 1 will be 2. This is my new value, pos, right? Correct? Now I'm calling maximum with 2. Pos now is here, right? The logic says, if pos is equal to A length minus 1, you're playing with a very small array of one element. So
that same one.
it will be the same one. So this guy will return A of 2. Right? Correct? Which is, yeah, you're right, it's 1. Right? No more recursion. There is no more recursion. You're returning an element directly. No more max right. You're doing no more recursion here. So you're returning 1, right? Now I will plug that answer here. This guy is 1. All I have to do is compare A of 1 against 1. Whoever is larger, that's the answer. In this case, A of 1 is 9. Compare versus 1, the answer here is 9, right? Now I'll plug that answer here, 9. And this guy says A of 0 is 7 versus 9, 9. Done. Is that clear? Yes? It's tricky,
I
right?
didn't understand that last part, but when I looked up.
You understood this one?
Huh?
You understood this part one,
Yeah, I
right?
should understand when I looked up again.
Okay, okay. take it from here. This is 1.
Right.
Now, this does not go any further down. This is done. This is a final answer. No more max right. You see? No more max right here. So I will use this result and plug it here, because remember, here I didn't know what max right was. That's why it went down. So I will plug this result here. So this is 1, right? So now I can finish this comparison to what's incomplete. A of 1 is 9 versus max right that you just gave me, that is 1.
Okay, 9.
The largest is 9.
Gotcha.
I can come back here and plug that out. The largest that from here that was 9. 9. Is A of 0, 7 versus 9. Which one is larger? 9. Done. No more.
That's what it's doing in the background. That's what you should.
That's all that is doing on the background. Yes. Is that clear now?
Yeah.
Yes? Recursion is good? You had a question, I'm sorry, you get one.
I was curious to get A dot length minus 1 with the actual value of the
Okay, okay, good, good, good. Okay, guys. Look, again, I don't mean to scare you.